D. This one's a little harder. You can get the first part, but you're probably not going to be able to do the diagram because I've never showed you the diagram. If we increase the temperature, what's going to happen?
Increased rate.
Have you ever seen the Maxwell-Boltzmann diagram?
I've heard of it, but I don't think I've seen one.
All right, so the Maxwell-Boltzmann diagram is showing the number of molecules as a function of energy. So here is the number of molecules. That's funny, you've heard of it, but yeah. Here's the number of molecules, and here is the energy. So Maxwell-Boltzmann said, basically, if you have an average kinetic energy, like you take a temperature, we would say that the average molecular temperature of this room would be room temperature or whatnot. It means that all the molecules in the room have an average of that. Are some warmer and some cooler? Sure. But if we were to take all of the spectrum of all of these molecules and average them, we would find that the average temperature should be room temperature. So nothing will have absolute zero or zero energy. So we will start here and we will make a curve. And that line will approach infinity as it goes that way. So that would be your distribution. The average temperature would be somewhere around here, right? Well, let's say that the activation energy is this right here. Not a lot of the area under this curve, not a lot of these particles have the energy required, right? We follow, and this is a pretty complex concept, but I think I don't think it's beyond you guys, but anyways. So the area under the curve, the number of molecules under the curve here, not a lot of them have that activation energy. So let's heat it up. Well, what's that going to do? Well, that's going to skew this line over to here, but it's not going to be over to here. The average temperature, it's not going to be this high because we're not going to be able to get all of those particles up to that higher average temperature, right? So the actual curve itself will flatten out a little quicker, but again, we'll approach infinity there. So the area under here is equal to the area under here, but how many more actually are past the activation energy?
More are under that barrier.
Right? So more are beyond this barrier. So the fact that increased temperature means more particles have the energy requirement. Very cool. If you did that, you would have gotten a 3 out of 3 on this, or actually maybe it's a 5-point question, but that AP question in 1992, you would have nailed it. There are 25 MCQs. There's 25 MCQs, and there are usually 2 FRQs. Multiple choice question, MCQ, FRQ, free response question. It's not, this is one of the free response questions. Yep. So yeah, I did a free response question today with the AP kids, and it took me 35 minutes to just show them how to go through it. Actually, it was kind of fun, but some of them are excruciating. This year, this 1992 one, that one's pretty cake, right? Yeah. They're not all that easy, unfortunately. All right, so let's we got, look at this. Who gave me kisses? This one of you guys? Somebody's trying to get a date to the prom, huh? No. What it's about? Yes, it's experiment time.
I think you're doing it, or
I'm doing it.
I kind of enjoy this just as much, except for the thing with the freaking machine.
Did you just cuss?
He said freaking.
With the what?
The machine, the barometer, no, what's the spectrometer?
You didn't like that loud?
It's not I didn't like it, the machine.
It was fun at first. But not really like,
That's basically to show you probably never want to be a research scientist. right?
I'd rather be like. So my favorite.
Research scientist?
Yeah.
Talk to him sometimes. Maybe he really loves it. But I did it for a summer and I was like, eh.
My mom did it all year round.
But what? Yeah, I'm kind of doing it this way to face this way, but if we take a look, here we have a test tube. I'm going to give it a rinse. One of the biggest parts of being a chemist is a lot of cleaning glassware. So in here I have, I'm going to put 5 milliliters of a starch solution in here. And I'm doing qualitative, so I'm not too worried about the quantities I'm using, but I'm trying to match these up.
Go ahead.
6 and almost 6. I'm gonna pour a little bit of this out.
Way too much.
Judging is boring.
Perfect. So if we take a look here, I'm going to pour this one in here. And if somebody would get a stopwatch ready,
Oh, 1, 2, 3,
I'll tell you when to
4.
start it.
5.
I'm
Oh,
not ready.
I'm ready.
wait,
You
wait,
got
wait.
this? Ready? Start it.
Oh.
Oh,
Oh.
wait, was that
So
just the top?
that was a very fast reaction. Did you stop that?
Skip.
1
It was like-
second.
Less than 1 second.
Like 1.2 around there.
Less than 1 second.
Very quick.
Very
What's the
quick.
starch solution?
Starch solution is just this reaction. Actually, you saw this in your biology class last year. Do you remember this is the potato one?
The potato.
Isn't it to test for like starch to the potatoes?
I'm sorry?
Wasn't that used to like test for specific like biomolecule in the?
Yeah, so it's starch and iodine create a black color like you saw there. So that was at full concentrations. So now what I'm going to do is I'm going to half the concentration.
It's gonna be slower.
Or did you say more? Oh, stop. Okay, got it. This time I'm on.
You're on it this time. He's on it this
I'm
time.
also on it.
Wait, tell me when.
Uh-huh.
Funny.
A little more than 6.5. Ready?
No.
Right on my finger. Ooh. Ready?
Oh my gosh.
Ready, set, go.
I'm so ready to quick that we laugh. I got it.
Boom.
10.21.
So that was actually about 1/3 of the concentration. Let's try one more.
Let's try 100th.
1/4 of the concentration.
So if we had very, but it's still within the entire.
If I make it.
Like a tiny drop.
This is Your girl is so bad.
What? It's so good.
Grey's Anatomy is good.
It's so good. You girl is so good.
It's terrible.
Okay, you watch me.
Did you guys notice that the girl from Grey's Anatomy is in
Yeah,
the,
I
the
noticed
reaction for this?
My friend, I was like, am I crazy or is this-
Miranda Bailey. Is
The Nazi.
that what they called her?
The Nazi.
that was so weird.
Why did they decide to kill her? So many contracts ended and they were like, okay.
McStreamy. There's a guy named McStreamy, which he just does like YouTube streams or something. There used to be a guy named McSteamy on there, right? McDreamy. But is there like a new guy named McStreamy and he's just like a YouTube
That's
streamer?
Smart, that's smart.
That'd be amazing, wouldn't it?
Great.
All right, 1/4 the concentration.
I'm insane.
3, 2, 1. Press it.
Oh. No, I wasn't.
Are you writing the publishers for McStreamy?
Yeah, emailing. copyright.
The McStreamy Award. Is that okay?
Maybe.
We're looking at water. I know, but it's a joke.
Iodine.
Iodine.
Huh.
You know what?
Did I miss for something?
Minute. It's up to a minute.
It's a minute?
Minute 3.
Minute 5.
Yes, time passes. You know this. Be true.
We'll let it go 30 more seconds. If we don't get anything, I might have messed up something. Maybe I poured from the same one twice. I
I
did-
have faith.
Gotta have faith, the faith, the faith.
So maybe not those, because if you said this is like one, what was it?
1/4. Yeah.
100th.
Yeah, so if the other one,
1/2 and it took 9. It could,
Then it would
it
be
actually
like-
can be, it can actually be exponential. Oh,
Oh,
there it is. Call it.
so
Start it. Stop
138.
it.
Yep. So there we
138.
go. So you can see that we can actually affect the concentration. I'm sorry, affect the rate by affecting the concentration. And in that video, she times that reaction. If you watched all the videos on Friday, on Monday this morning, or this past Monday, this beginning of this week, you saw her on the video. She was doing, is it Flight of the Valkyries? Dun, 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 or the 1812 Overture? Yeah. So she's playing that song, and whenever the cannons fire or the bass drum bounces, she's timed it out so that that will actually react at that particular time. Dun, 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 dun. Is that, yeah, that's the one that she does. Yep. Last one over here, it's Jonah, right? Jonah, why don't you hop over there? Just in case this can get a little bit messy. You've done this? Owen's done this.
I have. I did it for excitement.
Yeah, he knows. Come on.
Right?
Yeah. Actually, it's called Old Foamy.
Oh, I know
Wait,
this
I
one.
looked at toothpaste.
You know Old Foamy?
Oh, I know.
Hey,
it.
what?
I haven't done it, but my mom. But yeah.
Oh, I love this one.
It's elephant toothpaste?
Yeah.
No, that's a new fandangled name. Back whenever I first did this, it's called Old Foamy. Why do they call it elephant toothpaste? If somebody would record this, other than that, maybe we can get a nice video of this and I can post it on there. The devil's toothpaste?
That's the one Mark Rober did, that like exploded.
But I don't think it's ready yet.
It's okay. It's not going just now.
Okay.
So I'm going to, Leo's always ready. So I'm going to mix that up, that soap and that peroxide. And 3, 2, 1. Mix it up and back up.
That was so.
Yeah, that was.
Are you serious? It was cool, but it was very anticlimactic.
I like it.
What are you talking about? It's still going.
Yeah, it's cool, but I thought it was gonna shoot up. Yeah, like Martin Rover. Don't worry, I'll meet the video. I'll meet the video.
Like what?
Don't worry, I'll meet the video. You should watch Mark Rober's video.
Is that where he does this to a whole house?
He made a giant flask, like the
Then you
size
get
of
to
a
smell it?
building. Super big, like the size of a building. And then he filled it.
Yeah, but the bottom shot at it.
Yeah, yeah. Yeah, he had to use it. He had to do it.
Was his this cool color that I've got?
Right.
Yeah, right? Look how cool this is. You've got some yellows here and then this blue and the accents. Oh, it's beautiful,
Art, it's art.
right?
Da Vinci who?
Well, let's take a look. I don't know if I should put this on fire, but I'm gonna go for it anyway. But let's take a look here. Now, we know yesterday that oxygen was produced there. Take a look here. You can see whenever I put it in there, It
You are, it's so.
it is you can see it's reacting with that. Pretty cool. It smells like oh look, little gas pockets are popping.
Yeah, the smoke.
Yeah. But it's apple, sour apple. So I don't know why.
Now it smells like burnt soap.
Yeah, now it smells nasty.
I think it's just.
But that is Old Foamy. You can watch those videos. Some of them do it pretty cool. There's a guy named Science Bob that does one,
Oh, yeah.
and his shoots all the way up to the ceiling. I'm not dealing with making a mess that big in my classroom,
You could make a giant glass and seal it with like.
right?
tape and certify the kid with cancer for his 13th birthday.
Oh, yeah, it's a beautiful day.
What?
We can just take a flask outside and have a shoot up in the air.
This kid, I don't remember his name, but he's trying to give me unsolicited advice. Gavin, maybe? Is it Gavin? Yeah, it's Gavin. You guys were right.
Send it in group chat.
Yeah, send me the video. Are you gonna do it through share phone? No, I cannot get on a group chat with you. I did not want that. You guys hear me on the video? I did not be on a group chat with Leo. All right. My email is jjackson@msdwt.com. Okay, I can do airdrop. How do I do airdrop?
We can take you on.
No, thank you.
It's a worthy trade.
It's a worthy thing.
Alright, Leo.
Which of these do I touch for screen share or for?
Mine
You
just.
do have a good one.
Oh,
I don't
Ricky?
have my mask on. You might want it, so.
Is your iPhone's name?
What's that?
Is your name just iPhone?
That's, yeah, my name is just iPhone. Is that pathetic?
No, mine's Neil's iPhone, but iPhone's.
Oh, cool.
Yeah.
It's so funny. Now I have it? Cool, and then I can actually bounce it to this guy. Boom. All right, guys. Too much fun, so we have to end the fun now and go to the math, right? Page 8, I believe.
I'll make a big mess.
That's all right. All right, so rate law is actually probably one of the most demanding things when it comes to math. So hopefully your math skills are strong. Luckily for you, we don't do anything above algebra, but if you were going real heavy into these rate laws, you would have to do calculus and stuff like that, differentiations. So don't worry too much. We don't even do those really in the AP course. That's like probably 600 level college chemistry classes for majors. So we do figure out what K is. The general rate law for any reaction is just rate equals a constant K times the concentration of the reactants. So take a look here. There is something called a special order. And basically it is just a power that you take the concentration to. So ask yourself this, what happened between 1 and 2? What did we do to the concentration?
Doubled it.
You doubled the concentration. And what did we do between, what happened to the rate when we doubled the concentration?
Doubled it.
It doubled. If you're having trouble doing that math, you can always take the lower one, the bottom one, and divide it by the upper one. So 0.1 divided by 0.05 is 2, and 8 divided by 4 is 2. So now, to tell you the truth, this is how poor I am at math, but you guys, there may be a term for this that I'm not gonna know. But basically with this, we say 2 to the x, that order, doubled the rate. So this is a concentration to the x, the change in concentration to the x equals 2. Was that called something?
Well, you can do log 2 of 2 and then now you get x, but
So if we take log of 2 divided by log of 2, the log of this divided by the log of this, that can get us x, right? What is log of 2 over log of 2? 1. So the order for this is 1. So the order for this is 1. And we don't actually have to write it, but chemists actually like when you do. For this one. Because we have to write the concentration of A. If you don't have an order there, it could be like somebody forgot. And we don't use 1 whenever we say like sodium chloride, because you would not have wrote sodium if there was not at least 1 sodium, right? But here, sometimes you will write the 1. Good question, Claudia. Oh, I'm sorry. No, that was the placeholder at the beginning. What did I mess up? I put the order for A as 2 after I said several times that it should be what? 1. I don't know why I wrote 2. I was all about writing 2 there though. So now what we're going to do is we're going to write the actual rate law. So we need to calculate what K is. And to do that, we can choose any of these trials, right? So we can choose this last trial here. So 16 equals K times 0.2 to the first power. 16 divided by 0.2.
It's 80.
So that's 80. So the actual rate law is rate equals 80 concentration of A to the first power. And just to show you this would work, if I took 0.2 divided by 0.04 or 0.05, what would I get?
4.
4. And if I take 16 divided by 4, I would get 4. What is the log of 4 over the log of 4? Still 1, right? So it doesn't matter which of these trials I compare. I could also compare 2 and 3 and 8 and 16.
So the actual rate law is just substituting K for the actual number, basically.
Said that like you wasn't that impressed, didn't you? Yeah, the actual rate law is boring, I guess. Sorry. No, yeah, you're exactly correct. You're exactly.
Okay.
So if we take a look here, general rate law again, rate equals K, concentration of A, that's a bad concentration, to a certain power times concentration of B to a certain power. Yeah. So here's the key. This threw off 5, 6. Even their coolness could not protect them from this. If I look here, I want to find how A affects the rate. So what I want to look for is I want B to be continuous. I want it to be the same so it does not affect the rate because of the concentration of B. So I'm going to use trial 1 and 2 for A. 0.2 divided by 0.1 is 2. 4 divided by 2 is 2. So what is the order of A? Am I doing this too fast?
1.
Yeah, are we at a good speed here? Yeah, so 1. Now, what will I pick trial-wise to find the order of B? Experiment 1 and
1 and 3.
3. 1 and 3 because I want A's concentration to be the same. So 0.2 divided by 0.1 is 2. 4 divided by 2 is 2. What is it? 1. It is not always 1. So the order for A is 1. The order for B is 1. What is the actual rate law? Well, which trial do we want to use? Doesn't matter. Let's just use the first one. 2 equals K, concentration of A, concentration of B. 2 divided by 0.1 divided by 0.1. Is that 200?
It's 200.
Yep. So rate equals 200 A B. So what if I double A? Then the rate will do what? Double. What if I double B and keep A the same? Then the rate will double. Now there's something called the overall order. The overall order is when you add the 2 individual orders up. What is the overall order of this? 2. So if I double both of them, what will the effect be on the rate? Since the overall order is 2, it would
Be 4 times.
be 4 times. Yeah. generic rate law. Rate equals K, I almost forgot the K, C to the something, D to the something. So for C, which two trials do I want to use? 1 and 2, don't sound so excited. And what is 8 divided by 2? 4. So 2 to the x equals 4, or log of 4 divided by log of 2? 2. So this is second order for C. That means if I double the concentration of C, how fast will the rate be? If D is unaffected? It would be 2 squared faster, or 4 times faster, right? Because if we put 2C here, 2 squared, and then C squared, right? Order of D, I want to use 1 and 2, 0.2, I'm sorry, just 2. And 16 divided by 2 is?
Wouldn't you want to use 1 and 3?
That's, yeah, I said 1 and 3, but I said 1 and 2, but I did 1 and 3. Sorry about that.
Okay.
So here we have 2, 0.1 and 0.2, we doubled. And 2 to 16, I believe that's 8 times more. So what is log of 8 divided by log of 2, or 2 to the x equals 8?
3.
3. So it's third order. What's the overall order here?
5.
5. Yep, use Adam. So if we want to find the rate law, the actual rate law, we know that 16 equals K to 0.1 square times 0.2 cubed. I need a real calculator for this. I don't think the watch can do that. So 16 divided by 0.1 squared divided by 0.2 cubed. So that's 200,000. So rate equals 200,000. Concentration of C squared D cubed. And what this does is that means that if they say, okay, I want to rate this fast, you can come up with concentrations to put in here to figure out how you can get a rate that fast. That's what that lady did with the 1812 overture, right? She used concentrations to determine the timing of how many seconds it would take before the reaction would occur. If I took the overall, if I doubled both of these, then how fast would that be? If I doubled C and D,
32 times more fast.
32 times. It would be 32 times faster. It would be 2 to the 5th, right? What if I tripled C and left D to be the same? You're doing too much. If I tripled C, or yeah, 3 times C. So 3 squared is 9. If I tripled D and leave C, then it would be 27. Last one. They don't ask for a generic rate law this time. So there we have, this is doubled. This is doubled. So the order of A is 1. This is doubled. Oh, I can't do that. I have to do 1 and 3, right? This is doubled, and this is 1. What's the log of 1?
0.
0. 0. Log of 1 is 0, so it's 0 order. What does that mean? If we change the concentration of C, that means it's not going to do anything, right? Because anything to the 0 power is 1. So it won't affect it. So the concentration for C is not effective on this rate of reaction. So the rate law will be rate equals K A to the first. We could stop there. Some people might like to see that C to the 0 power. Totally up to you on that. What will the rate be if A is 0.25 and C is 0.50? Well, we got to find K, don't we? So let's go ahead and find K real quick. Ignore C. And let's do the rate of 2 equals K 0.1 to the first. 2 divided by 0.1.
It's 20.
So K equals 20. So we get 20 times 0.25 to the first times 0.50 to the 0, which is 1. 20 times 0.25,
The answer is 5.
5. The rate equals 5. That would be 5 molarity per second. K's units change, so a lot of times we don't bother with them in first year chemistry. K units are different depending on the orders of things. All right, doubling the concentration of a reactant increases the reaction 8 times faster. What is the order of the reaction? If we double it, it makes the rate 8 times faster. So what is the order? Third order, or 3. Questions there? This is actually the last part of this unit, is to be able to use these and manipulate these. This unit is pretty quick. We'll probably be testing on Thursday. Next Thursday. I would like for you to do problems 1 through 5. And the reason why I want you to do 1 through 5 is so that we can try to get the lab on Friday. If we don't get the lab on Friday, that messes up so much stuff because of the asynchronous Monday. It really screws us around. So hopefully we can get the lab on Friday. At worst case scenario, at least we get the data for the lab on Friday, and you guys can chug through the numbers on Monday, asynchronous day. The laboratory, basically, you saw the one where I made the iodine and you could not see through it anymore. You're going to make a reaction occur where you cannot see through it anymore. You're going to make several different concentrations, and then you're going to time each one of these when you put them together, and you're going to log the time, which will be the rates, and the concentration, which will have molarity. And then you should be able to get molarity per second and find the order of the reactants. So it should be pretty fun. And then if we find like it's second order or whatnot, we can see the curve on it. If it's first order, every time you double it, the rate doubles, right? So it should be a straight line going up like that. With a second order, it should be exponential, right? The cool thing about these rate laws is that K is actually the slope dependent on the order, the slope of a particular line. And I don't think we need to get out of this first year. That's what I got for today. Any questions?
So our test will be probably next Thursday.
That's what I would say. For now, tomorrow we're going to go over the answers to these, and then I'm going to discuss the laboratory with you. Why not? Are you guys serious? Hey guys, I don't have anything more for you. If you want to stick around and ask questions, you're more than welcome to. Other